Okay. Hi everyone. Thanks for coming. It's a great turnout today. Um, so today's Blackboard speaker is Alicia Savelli. She's a grad student at the Department of Astronomy and Astrophysics here at U of T. Also works with folks at CITA. And she will talk about plasma physics and hydrodynamics and teach us a lot. So over to you, Alicia.
Thanks. Yeah, so I'm going to be talking about something I've been working on with Bart and Norm and Daniel Rochelle at Leuven in Belgium. So I'm going to be talking about this subgrid model that we've developed for radiation in our MHD simulations. But to start from the beginning, what I'm trying to model, so in AGN or XRDs, you have the central black hole, and then you have the accretion disk around it, and then you have the jet coming out. So this is your basic picture of what it looks like. But then there's some region, we don't really know where it is. It could be like here, or here, or maybe here. Not really sure, but it's very, very hot and very low density plasma, and it emits X-rays, and that's the region that we call the corona, which by non-surface definition is just literally where the X-rays come from. And so the mechanism that we believe produces these X-rays is inverse Compton scattering. So that's when you have an electron, relativistic electron, very fast moving, goes and up scatters a photon to higher energies, X-rays. So that's one mechanism we believe in producing the X-ray emission. But we actually think now that it's not necessarily single electrons, because the electrons in the plasma are actually, their temperature is only around 0.2 MC squared. So they're not super relativistic, but we think the plasma as a whole, like the bulk motions of it, is actually what's going and upscattering the photon. So if this plasma bubble is moving with speed v, again, it goes and upscatters the photon. So this is what I'm trying to model in my simulations. So I said that the corona is really hot. And one of the mechanisms we believe keeps the corona is magnetic reconnection. So that's when you have two anti-parallel magnetic field lines, and if they get dragged inward with the plasma, then they pinch off, break apart, reconnect, and shoot out a bunch of heat, energy, plasma, and the plasma that shoots out has sort of a bubble form. It's called a plasmoid, and this is what we think might be some of the plasma blobs that are upscattering these photons. And then this region here is very important. It's called the X point, and that's where the reconnecting of the field arm is actually happening. And it's very, very hot there. So we basically want a subgrid model that will capture this motion of the plasmoid. So that's going to be going really fast. So we should have a v squared somewhere in our subgrid equation, I guess. And then this region is really hot, so it should have like a t squared somewhere in there. Right. So some of other characteristics about this reconnection layer, we call it, or a current sheet, because since you have parallel field lines, like this is a parallel current. So we say the current sheet has length L, and then it's going to have a width delta. Then there are a couple of different theories you can use to describe plasma. So one is kinetic theory, and the other is fluid theory, or MHD. So with kinetic theory, you're basically modeling not like exactly particle by particle, but you're modeling the particles as a distribution function. So with some position and momentum. In fluid theory, you are approximating the plasma as a fluid. So you're basically coupling Maxwell's equations with John Ryder a few times. Faraday's law, and I'm also keeping all of my C's because I get a little worried when I can't see them. And then Ampere's law. Gauss. And then no magnetic molecules. So this plus hydro gives you the MHD equations, which I'm not going to write out because they're long and not super relevant for the math I'm going to show you anyway. But what's important to know is that there's 3 conservation laws. There's one for mass, 3 for momentum, and 1 for energy. So use all these equations in an MHD simulation. So the next big difference between these two that I want to talk about is that the kinetic simulations, since they are the simulations we call them particle and cell, because you're modeling not individual particles, but like blobs of particles. And it's very expensive to do on larger scales. So you can really only model local scales with these. There are some GR fixed simulations where you can model a black hole, but you're not zooming very far out. And then the nice thing about the fluid or MHD simulations is that you can model global scales. But the problem is it's not as physically accurate. So this is solving the distribution function, right, which is like real physics. And this is still real physics, but it's there are approximations and you have to use more subgrid methods and so on. So what I'm trying to do in my project is to kind of bridge a gap between these two. So I'm taking basically a cutout of the corona, I'm ignoring the black hole, and then I'm modeling that as a single reconnection layer like this that has all of the properties of the corona that have. So that's what I'm doing. I'm doing it in both these fixed simulations and the MHD simulations to try to see if, yeah.
I'm just trying to get some intuition into the 3rd dimension, into the board of your cartoon of what you're calling a layer.
Yeah.
Is the layer in the direction into the board?
The current would be going out to where? Yeah. So, my simulations I'm doing 2D, but in 3D it would be like a sheet of current. Yeah. And then
what would be the dimension into the board direction relative to L and into L?
Like how big is it?
Yeah. Is a platform going to end up round or is it some other?
Yeah, that's a good question. So, it kind of depends. Like you can't have long current sheets, like in the global simulations, like the one that like Bart does. Like sometimes you see it. It's basically like a disc around like a thin disc. Does that make sense? Like around a current, basically, like a total current. So it could look like that, or sometimes you see it in like turbulence. Where you have like 2 little blobs coming together and then their magnetic fields are opposite ways, so they have like a little friction between them. So it kind of depends on like the problem where it is, how big it is. The plasmoids, they aren't necessarily little bubbles. They could be like cross sections of like we call it flux tubes.
Yeah.
So they could be cylindrical.
Can I just add that they are, at least in the simplest case, they're going to look like these flux ropes through the 3rd dimension, and they have some helicity because they have some current that goes along the flux ropes like this. And the extent of them is going to be set by another instability called the kink instability that essentially If you have a tube and you have a slight perturbation, it's going to go unstable at some point. It's going to kink unstable, and that sets the maximum extent in the third dimension.
So that this kinky cube, all move at one velocity? Or
Or
is the,
What's your question?
does the whole tube in the downstream velocity of the plasmoid, does the whole tube move at that downstream velocity? I would say so.
There's a distribution of plasmoids moving at different velocities, which is,
I think he's asking if one,
He's asking if that whole tube is moving across
or if like parts of it are moving at different
in
speeds.
the 3D.
well, once it goes kink unstable, the tube itself becomes turbulent.
Oh.
So then there's some random motion, but in 2D, if you take the 2D approximation, it would mean that the whole tube would move with the same velocity. Yeah.
thanks.
Don't have to. So. Anyone in the way? Like online, I mean?
Yeah.
Oh, and they hit me.
Question for the people online. Can you hear Alicia clearly? Yep.
Okay, oh. Right, so the simulations I'm running right now are just, I'm just thinking in 2D right now to see if, my cooling mechanism works, and then I'm going to look for 3D, but those are valid questions. So yes, I'm modeling the plasma, this whole setup in both, kinetic simulations and fluid simulations to see if, fluid theory is able to like capture the macroscopic properties of kinetic theory, and if it is, then that means that we can use this mechanism in a global simulation to more accurately model the first quantum pool. So the final big difference between kinetic and fluid simulations that I want to talk about is what value they have for the reconnection rate. So the reconnection rate, beta rec, is basically the inflow speed divided by the outflow speed. So it's how fast the plasma is moving into the X point versus how fast the plasmas are leaving that way. So in there's this something called the Lundquist number, which is the ratio of like the effective time scale to the diffusive time scale. So it takes this form. So VA is the alphane speed, which is how fast things are moving, basically. The exact expression for it is this. Or sigma is the magnetization, which is the ratio of the magnetic energy to the resonance energy. So basically how strong is your magnetic field, like how do you want to be a very magnetic, very strong magnetic field. L is like how long your current sheet is, or whatever scale. And then eta here is your resistivity. So there is a way to show analytically, which I want to will take a long time, that the reconnection rate here goes like 1 over the square root of this Lundquist number. So that means if you were to plot beta rec versus S, you would have like a power law like this. But then the thing is, we found empirically through measuring it in simulations that an MHD, once you get above a critical Lundquist number of 10 to the 4, your reconnection rate actually asymptotes to 0.01. So that's been shown in simulations that like no matter what your Lundquist number is, if it's above 10 to the 4, your reconnection rate will be 0.01, which is good because astrophysical plasmas, their Lundquist numbers are much, much higher than 10 to the 4, but in order to simulate that, you would need insane resolution to model like 10 to the 20. So basically, as long as we're greater than 10 to the 4, we can trust that. But the problem is that in these pig simulations, the reconnection rate is actually measured to be 0.1, so it's 10 times faster. And so it's reconnects 10 times slower in MHD. But we have found a way to actually fix this. So the way that MHD simulations with resistivity have been run so far is you're sort of treating this data as uniform. So like everywhere in this current sheet would have the same data. But what's actually happening is these X points are charge starved. So that means that the charges move in really, really quickly and then they leave really, really fast. So the density here is actually very, very, very low. And so since the density is low, that means your current density, which would be your number density times your charge times some speed. Since the density is very, very low, but the current is very, very high, your speed is very, very high. So in the limit of a truly charged starved X point, you're actually traveling at, your charges are traveling at C. And since there's two species, there's electrons and positons, it also amplifies by 2. So if you use this charge starvation and implement it in the MHD code, part of it, then we actually see a reconnection rate of 0.1, which might be the long place number 10 squared. So this asymptote actually shifts up. And that's because your Ohm's law in ideal MHD, which is without resistivity, looks like this. But when you incorporate resistivity, you have this extra term. And so this is the E non-ideal or E star, we call it. And if you use this and then plug in this, and plug this back into the Lundquist number. So over eta, you solve this for eta, you would get and then if we write this number down to be as a mass density, we then we're left with this parameter here, which we're calling 1 over delta. So it's the mass to charge ratio, but we can't use the real mass to charge ratio because that's huge. So what this is saying is essentially, as long as you choose a mass to charge ratio such that your Lundquist number is bigger than 100, you will get a reconnection rate of 0.1 with this charge starvation. That's the important part. So that's a really big deal. And I use this charge starvation model in my radiation scheme as well in order to reproduce the kinetic theory, which I'll show you now. So I'll start with how we model inverse constant in kinetic theory. So basically, in these PIC simulations, the particles move according to the Lorentz force, and radiation is just modeled as a drag force subtracted off of the Lorentz force at each time step. So this equation describes that. So this is the constant cross section this is your background, energy density of the radiation field of photons. So we choose for now to just model that as, isotropic monochromatic radiation field. And this is the particle length factor because again, it's a particle simulation. And then beta, that's just V over C. So if you subtract this off of your Lorentz force at every time step, you will get, this is how you model the momentum losses in kinetic theory. So we can rewrite this in terms of a characteristic Lorentz factor if we choose to balance basically the acceleration that the particle feels from the electric field, like in the reconnection layer. So that force, I'll call F ref, I guess, is, that's basically QE, right? So E ref. Then an expression for E ref. So, you have, the inflowing plasma is traveling at a speed V in, we said. So that is an E cross B velocity, which means that if you have your magnetic field and your electric field perpendicular to each other as they are here, then your particles kind of drift in the third direction, and that velocity drift is described like this. So since our V in, that's Y, you can work out that this is and then we can cancel these. And B squared is just BX squared because we're up here where the magnetic field is in the X direction. So you can say that V in over C is basically E at EZ, which is your V ref, over VX, which is your upstream magnetic field up here. So V in over C, this is basically beta ref because the outflowing plasma is, as I'm traveling at this speed V out, and it's basically going at the outgoing speed here, which is essentially the speed of light in our conditions with our magnetization. So this is beta ref is basically V ref over V naught. So that means here I can write V ref as beta ref V naught. So this is the force or like the acceleration that would come from the plasma as the particles being accelerated through that electric field. So if I balance this with this, so if I set these equal, so I dropped the beta because this is the limit where everybody can basically at C. So we just set that to 1. And then this, instead of gamma E for electron, I'm calling it gamma rad now. So this is the characteristic Lorentz factor where these two balance. So it's like all of the energy from the reconnecting field is going into accelerating up to this gamma. So if I take this equation now and I rearrange it to solve for U rad, I get something like this. No, I get that, not like that. I'll get back into my drag force. So this gives us essentially the same drag force, but now I've reparameterized it in terms of this gamma rad. So this gamma rad can then be used to control the strength of the cooling. So if this is really, really high, then your momentum losses will be smaller and you'll have weaker cooling. So that's how it's done in kinetic theory. in MHD, it kind of makes more sense to think about energies. So if I do the same thing with an energy balance instead. So if I think about my current sheet, I want to think about the energy flux into the sheet and the energy flux out of the sheet and balance those instead. So my flux into the sheet is basically going to be a pointing flux divided by 2. And the reason we divide by 2 is because we find out half of the energy is actually dissipated into the sheet, so only half goes into the.
Is that an empirical result? Yeah, so it could be any factor.
No,
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 it's analytical.
it's the tension of the field pushes
Oh, okay.
out.
So it has to be 1/2, it can't be 1/3.
It's, I mean, it has to be, but around one, I can see.
And empirically confirmed, as in by confirmed by simulation.
Yes. Okay, thank you.
Okay. So the pointing flux is what the tube is this. So that's your flux. Oh, I should have said that. And then your outward flux. So this is essentially your inverse constant power times your number density times delta, which we said is the thickness of the current sheet. So the inverse constant power is and there's a C. So we're going to do that.
I think it comes up to date.
Where is the C? Thanks. And then the delta. So I want to balance these, but I don't have an expression for delta yet. So for that, I'm gonna go back to our charge starvation model. Remember I said for charge starvation, the current density is 2 NEC. So all of the charges are, it's still in all your charges are moving at the speed of light. So if I combine this with Ampere's law, and then use the fact that partial E by partial Y is essentially E naught over delta, then I'm left with this expression. So if I plug this J in for this J into Ampere's law and solve for delta, I get delta is 8 pi E naught. Now I can use this and this and this to write that energy balance. So I would get that's much more fun. Sorry. I can cancel some stuff. And then this E cross B, which is here, is again E correct and B not. So yeah. E rect times E not over 8 pi, and I said E rect, that's A rect, E not. So that's this now. So now I can write this, if I rearrange like this. This is now exactly equivalent to this balance that I wrote before. They're exactly the same. So what that tells us is with this charge starvation model, this, if we use this, we can exactly recapture the kinetic cooling with MHD, which is very exciting. But the only thing is now I have this gamma squared, which doesn't make a ton of sense in MHD, but yeah.
Oh, I don't want to, when you're done with this section, I'll ask you a question.
Okay, that's great. But, gamma squared is 12 theta E squared, which you get by averaging over the data you will get this out. Where theta E is the dimensionless electron temperature, so that's KBT over MC squared.
What's your okay, I should ask now, what's your magnetization in this outfield?
In my simulations, I'm using 15, but the corona is not.
Well, not in input magnetization, but after any of these converged particles. I'm asking because
It's the upstream of the.
so you're focusing on in this content
Mhm.
as an example,
Mhm.
but I mean, there are circumstances, of course, where the radiation and density north of the magnetic energy density. But like near a black hole, which I assume you are in this, that won't be the case. So, I mean, first question is why are you focusing on Indus content as opposed to single block? Because the pitch angle distribution is very concentrated along the magnetic field.
All of this can be done again with synchrotron, and we're actually going to add that into as our next, we have on
Okay.
undergrad that will likely help us.
Yeah, I guess the question though is why focus first on Indus content?
To do one at a time,
Sorry.
to do one at a time, but also because we believe
Well,
that all optimization is.
it's a good rule of thumb, right?
Yeah.
The ratio of the energy loss and its content. The energy loss for the magnetic field is greater than the photon. If the pitch angle distribution is probably like loss. Right, so they have significant gyration running. If they're moving along the magnetic field, well, there is no significant. Actually, I had a paper in that the first 20 years ago, but a different heating mechanism balance with in this time injects volume. We know the radiation process, partly line house. In that context, there's a real reason why you expect concentrated electron to be stable along the magnetic field, right? I mean, fire instability won't be perfect. But here, why won't fire blaze, you have a very concentrated particle flow along the magnetic field. The energy density in the particle is constant, then density in the magnetic field. The particles start heating up. And first.
I think the answer comes simply from quick simulations by Gorgel and Sridhar and Zironi applied to coronal conditions where they argue that inverse confidence is dominant
In what conditions? In black hole.
black hole corona, heavy corona.
No. Actually, you're right. I mean, thermal electrons cool very fast. The Compton scattering in this model is by bulk motion. these are by turbulence or by motion of the plasma. So,
Right, which yeah, that's good.
so,
That's,
so, depending on magnetism with corona,
well, it's not clear whether the mean, I mean, for everybody else, still getting to the, but, I mean, bottom line, you got this turbulent plasma with a magnetic field tied to the charge particles. And then this is immersed in some, maybe X-ray radiation. And so near a black hole, for example, you see a non-trivial distribution of X-rays coming out. And it's been a long-standing problem, exactly how is that non-trivial distribution produced. Multiple scattering of electrons is pretty well established to be the underlying mechanism, and how are the electrons actually either is a collective motion as Lear was just describing, or is it a thermal motion? And detailed particle cell simulations are now being done on the lines of what you're doing, what you decided to do. And you can get one result where, well, you shake the plasma and it's mainly the motions that are producing helping between the photons and the electrons. Or these chaotic motions can then cascade down in the Kolmogorov-like manner, the thermal motion in the electron. And what you get depends on the details of what's happening collectively, on the high magnetic scales, where the magnetic field and the particles are very close to each other, like where shear flows are, for example, rising in some cases. So, and then this tangled magnetic field has reconnection sites, or we have very large scale reconnection sites, like part simulations of the and so then, yeah, there's this debate about how much is heating is going to be reconnection versus the waves. But, I think partly the reason why I was asking this is because when you do ab initio calculation of the reconnection and get out of it, and when you make some reduction, you can measure it in detail. What, say, the distribution of the particles is respective. But in practice, the industry company is operating on very large line scale. That is what you would realistically simulate, in a average calculation. And so then it remains open question, what the particle is doing in large scale. That's partly why. Yeah. Sorry. I hope someone thought something. So yeah, in response, we only operate in very large scale compared to plasmas.
Okay. We are
Sorry, I'll shut up.
In the next line, I will write. I ran a liquid. What did I say?
We're going to temperature.
So instead of gamma, we use temperature, which is the average over the distribution x to get this. Right, so we're able to exactly reproduce kinetic simulations, but I haven't said how we're actually modeling this in MHD. So for that, I said that MHD solves these conservation equations for mass, energy, and momentum. So instead of like losses subtracting with like a drag force, here we have a same term where we subtract energy and momentum at each time step on our energy and momentum equations. So the same term we use comes from Amir, actually. So thank you for helping with that. This is the only one that I don't have memorized, so it's long.
No, I mean,
This same term, model is independent losses. So to get from this to our equation that we plug in the sheet, what's here is the constant cross section, P is your momentum, A is your wave vector. This is your, distribution function of the particles, which is modeled the Maxwell distribution. And then for the photon distribution function, we treat it as an isotropic radiation field, as we did in the kinetic case as well. And so that means that basically our energy momentum tensor takes this form. And then this is for x, y, and z at this point. And so if you plug all of that in, and do another hour of algebra, or more, if you allow, you get what we're actually plugging in. So I look at, this is index notation for anyone that's not familiar, maybe some of the summer students. So in like relativity, you got 3 dimensions of space and one of time. So we use this index to tell which of those equations we're talking about is time or space. So I'll have a spatial component. Sorry, this one's time or energy in this sense, and then this would be the spatial component. For the interest of time, I'm just going to write the energy sink, which is this. Was this too low, or am I okay? Thanks. So what this is now, we have the U grad again, and then we have the mass density, the delta that I said was that charge to mass ratio, which we don't have to be exactly true, we just have to have a line number of 100. This big capital gamma, that's the Lorentz factor of the bulk motions of the plasma. And then this beta gamma, beta sub gamma, is the velocity of the bulk motions. So now if I do the same thing I did in PIC, then I use the U rad I get from this balanced to reparameterize here. I get my final equation, which is so that's a lot of letters, but basically what's important here is we do have this theta e squared. So I said we wanted to look for a t e squared somewhere to capture where it's really, really hot. So that would be like your, this type of inverse of particles. And then we wanted a term that was like v squared to capture the bulk quantization by the plasmoids. And that is here as well. So I have both of those terms, and it's normalized by this theta rad, which is goes over to the gamma rad that we talked about for kinetic theory. So to recap, there's one little thing left that I want to talk about if there's time, but I'm trying to model inverse pumping, cooling in both kinetic and MHD simulations. We're able to get the right reconnection rate for the using this, charge starvation theory. So that now the reconnection rate and both simulations match. In kinetic theory, in Wisconsin, cooling, or like I said, equivalently, I do this for synchrotronus and cell phone or anything. The, is modeled as, radiation drag, which is subtracted off the Lorentz force. We reparameterize this by this characteristic gamma rad, which now controls the strength of our cooling, which is the next thing I'll talk about. Then I did the same thing in MHD, using the sync term to subtract off the energy in the equation in MHD. So that's what I've done so far. The only thing I haven't talked about is what this gamma rad or theta rad actually means. I said that it controls the strength of the cooling. Do I have like 5 more minutes? Yeah,
9-ish.
9 more minutes. I don't know. Or I could stop and do questions instead. I don't think there are some. I don't know what that. Let's put it on.
Which sort of cooling strength are
Oh. So there are 2 sort of length scales that are important in this problem for the cooling strengths. The first is the scale of the X point. So cooling that's happening in here. So the X point, the length of the X point is essentially the plasma spin depth. So the plasma spin depth is kind of like, you can think about it as like the charge separation in the plasma. If I had like one charge and I took an opposite charge and like displaced it slightly from that charge, it would like move back, but it would like overshoot a little bit, and then move back again, and then it would oscillate. So like the distance of it oscillate, like that amplitude is the spin depth. God, I'm so sorry, no one. It's still on. I'm
It's
so
on
sorry.
anyway.
Okay. Okay, it's in my hair, and like, which. This. So basically the particle is accelerating over its length, and the energy they pick up accelerating over that length is, when you use that for I guess. Times the distance. And then the kinetic energy that they get. So it's, of course, gamma and c squared. So if I balance these 2, set them equal, and solve for gamma, I get this. So everything here is a constant. Wait, no, that's not true. But I was trying to say this here. Yeah. This is what we call that sigma of the magnetization that like Chris was just talking about, and that I said goes into the alpha speed. So basically this Lorentz factor goes like the magnetization. So now we can say that typical electrons that have this gamma E, if our gamma rad, so one that we're using to control the cooling strength, is much bigger than gamma E or sigma, then that means that you have weak cooling, because like you're saying, the actual Lorentz factor your particles are traveling at are way smaller than what they need to like radiate efficiently, right? So they're never going to get to the point where they're radiating a lot. So that's weak cooling, and then of course when we're also to with gamma rad is much smaller than gamma E, then basically they're all traveling faster than this gamma rad. So they do radiate strong. So that's the first scale. And the second scale is over the whole length of this sheet, so that's the advection. So I guess, so here we compare the advection time to the cooling time. So the cooling time is given by this expression. FRC is so this is and then the other is the advection time, the other time scale we're thinking about, which is really just given by the length of the sheet over how fast the plasma is moving, which is at the alkane speed, which is essentially the speed of light in our relativistic case. So that gives two more conditions. If your cooling time is much shorter than your advection time, then that means you're going to cool strong motion. And then if your cooling time is way longer than your advection time, then they don't really have time to cool, so you're cooling weakly. So if I combine these and these, I'm left with 4 situations that I'm generating. So the strongest cooling, that's when gamma rad is much smaller than sigma. So I have to choose a gamma rad that works for this. So the sigma that I'm using in my simulations is 15. So I'm choosing gamma rad of 10, and then if you do the conversion, that gamma rad squared is theta rad squared, that shows 10. That's not what this is. 14.14. The next case, we're calling it moderate cooling. So that's when your gamma rad is now bigger than sigma, but your cooling time is still smaller than the advective time. So the gamma we're choosing for this one is 15, and this is 21.21. Then we have weak cooling, which is the last case where the cooling time is much longer than the advective time, which achieving 60 and 84.5. And then of course there's no cooling at all, which is when both of these are essentially finished, or I just don't cooler. Right, so that's the last thing I wanted to say. The reason we did this whole gamma rad and theta rad parameterization was so that we could figure out a way to control our cooling strengths so that they would match in both PIT and MHD. And these are the 4 cases that we look at and are simulating them. Yeah, that's what I have.
Do we have questions for Alicia?
Can I ask about, I guess, how much freedom you actually have to move around the undergrad? Because presumably like that controls the radiation background, the background radiation density. And so is that just an unconstrained thing, or would you expect like a typical radiation density, like radiation or whatever?
That's a good question. I don't think that is all. Or
You can not necessarily simulate the exact value. It will also not necessarily be the same for every black hole that you're looking at, or XRV versus an ATM. So what you do is you choose the regimes that are likely applicable. The no cooling regime is the benchmark. And then depending on your situation, on what is the background radiation field, what's your typical magnetic field strength will be in a certain region. So you simulate all the regimes and you
Well, the background radiation field is constrained, at least for the hard state, it's constrained by observation. It cannot exceed a few percent of the total energy.
an XRB. Right?
For XRB, for hard states, I don't think there are any events for hard states in AGN.
Yeah, exactly.
In AGN, you also have to explain, you can, resolve the big bond. It's the UV bond, and then there is an extension. There it's a bit more flexible. So it depends what you want to experiment with. But for the hard state, it's very, most of these models designed to explain the hard state. It's extremely constrained. You know, not only that, but also the optical electric, the corona. So it, in my opinion, it's a bit fine tuning. It needs to be like not more than 50% of the energy in the corona. And the idea is that the artificial proceeds in this model that in all the fiction box peak simulation, you just do it by hand. No.
The uncooled ones are matching exactly. As in,
how, okay, but in the image, what are the two families? I mean, we just say you have an image, something like, this image. Okay, so you have the right answer. This way.
We're using ours non-uniform.
Oh, yes.
Just
you-
finish
you
that.
usually have syllables. Not got it, right?
Yeah. It's always saying.
And how many free parameters does that have? Does that just have one?
We'll take like the delta, or I guess the sigma. And not.
Well, yes, I'm asking is when you say, okay, suppose it results in a U, and you told me that results in U. Is there any conditioning on that having two frozen basically planetary in managed using you get or
we discussed yesterday, you have to choose a skin depth such that your Lucas number is above 100.
Yeah,
well, I mean, when you're simulating particle cells in the full kinetic simulation environment, you have eventually the situation. So it's multi parameters other than what the actual is stable. On the NHP side, it's a bit more ambiguous, but no one understands it's still maybe not understands.
You get a skin depth, like she wrote it somewhere.
Yeah.
Your resistivity translates to a skin depth, so that constrains you.
Yeah.
That you can choose relative to your box size, but that's a numerical argument rather than. What we found is that if you choose, let's say in PIC, you typically do say 1,000 skin depths in your box. In MHD, we do the same by choosing this MO3, this delta parameter. And then we need the same resolution in MHD as in PIC to resolve that skin depth, say 5 south per skin depth. And then your results are the same between PIC and MHD. That is for relativistic sigma, so sigma above 1. Sigma below 1, I cannot guarantee that.
So then in a global simulation, you rescale this as global peak.
The neat thing is that you need that skin depth requirement results in a Lundquist number of 100 that you need, or anything above 100. But to do reconnection globally in MHD with the uniform resistor, you need a Lundquist of 10 to the 4. So your resolution requirement softens by a factor of 100. So you do MHD compared to PIC, which makes it cheaper, and your Lundquist number going down, your critical Lundquist number going down by a factor of 100 makes it cheaper compared to uniform resistive MHD.
Any questions online? For the online people? Still a few people there. I don't think so. Maybe we give Alicia one last round of applause. Enjoy the rest of your day. Now you've learned about reconnection. You've been empowered. Welcome to the club.
Do I have to erase this?
I think that's Melon's job apparently. No, I'm just kidding. That's not.
Right. It's like, what's in there?
Yeah.
Okay, so I don't want to-
I don't think.